Yes, hello? Yeah, I think now it works. Okay, so this is really a short presentation. I'll try to catch up a bit on the delay, just to report about what we are doing with Samba. Here the context actually is kind of a bit more general. It's about our move of the storage to EOS as the kind of open source based storage for home directories. We've been running DFS, Windows DFS at CERN for many years. This is now going to be phased out. So we already started actually a migration of users from Windows to CERNBox as a home directory place, which basically means that we are going to get more and more Windows-based use cases on top of EOS. And obviously, a Samba gateway, so the ability to map a network drive in Windows was required immediately. So this was already done. It's a few years that we have a Samba gateway that was put just to test a single machine. And since last year, I started to work into a high-available cluster using the Samba features. I mean, there is a daemon provided by the Samba software which allows to run in cluster mode. So this is now all done and all in production. And we also had to do some performance measurements to compensate and see what to expect from this kind of deployment. So now this is indeed all in production. We have our own terminal service, which is based on Windows, where this is mapped permanently. So in terms of architecture, what does this mean effectively? It means that Samba itself as a daemon to run in this clustered mode requires what is typically called the floating IPs, so virtual IPs that can be assigned to machines. And this is provided by the network team, and it's not really a big deal. And also a shared state on a shared file system, which sounds a bit strange, like to provide a shared file system, you already need a shared file system. And to avoid to be in a loop, we are not relying on EOS itself, but on CFFS. That is a very, very small volume shared across the machines running the cluster. And this is where they kind of keep the state, the shared state, because the protocol itself is stateful. So you need some place to share the state. So the solution in the end has been to have indeed a very small, it's really a very small mount point on at the moment we have 4 machines running this, and all of them mount EOS with FuseX with exactly the same software that was being presented already by Andreas and others. Yes, so this is basically where we are. And of course, we have to do a bit of juggling because the Windows domain requires its own way of handling this. And so then we have to join the domain using those floating IPs, because we present ourselves with the floating IPs, not with the IPs of the machines. So it's like changing identity in a way. So, but fine. I mean, this is actually pretty much done. So where are we now? We are basically in good operation, let's say, and I see over, this is like a couple of months of usage. This is the Christmas break, but then apart some peaks, there is a kind of permanent growth. Here we're talking about order of 500 clients permanently connected over time. This is sampled every minute, and I see 500 independent active clients all the time. And we also already had to have some interventions, and this is actually working pretty nicely. I mean, the floating IPs are reassigned seamlessly, so the clients don't really see anything. I mean, if you are really transferring a file on that IP, you see a disconnection, but then Windows itself proposed to restart, and it will. And that IP has been maybe reassigned to a different host, and everything is OK. So far so good. What are the problems? So this was already mentioned this morning. ACS, Windows ACS, and how to map them into EOS. We are working on this. So there is already work done by Rainer. Actually, Andreas mentioned it this morning. So to basically expose via Samba the EOS ACLs so that Windows can see them, and then we can have the two. This is not yet in production because we need to rework a little bit also what this means in terms of CERNBox shares, which is not exactly the same concept. So we have to work on this a bit, but basically the software is already there. There is a library called the Rich ACL for Samba for that. And the other part, which is also a source of headache recently, we've been working with Andreas on this, is a case which is quite recurrent, actually, given the usage. So this is people, administrations, and even people, physicists, etc., working on Office documents via Windows. And it just happens that if you have multiple people trying to access the same file, if they access it via different gateways, then the notification of this file is already opened by the guy X doesn't work, which means that eventually you have two users ending up writing the same file and not knowing that the other one also has the file opened. And the last one that saves wins. And so you lose data, effectively. So we are looking after this because it's kind of critical for the use cases we have. There is actually a fix in the pipe. Actually, on a preliminary test that I did just before this presentation, just wanted to report on it. It doesn't yet work, so we still have to work, really understand what's behind this. And it's all about how Microsoft Office deals with these kind of things. So this is all I have. Thanks for, as I promised, it was very short just to give a bit the status where we are. So thanks a lot.
Thanks, Giuseppe, for the catch-up. Are there any questions to Giuseppe? So if not, we pass to the next speaker, which is Mihai, which is going to talk about XDC developments, quality of service, and the converter engine.
Okay, thank you. Okay, hello everyone. So first of all, my name is Mihai Pătășcoiu, and for the last 2 years I've been working on EOS as part of this XDC project, which I would like to first just say a couple of words about it. So XDC, so-called Extreme Data Cloud, is a 2-year, is a 2-year EU-funded software development project. It also has multiple partners, and one of those partners is also CERN. And the project we're working on is EOS. It started in February 2018. And the goal is to improve existing data management services by adding missing functionalities. Okay, but more concretely, in this talk, I will discuss QoS developments. The people involved here at CERN at EOS would be the ones on the slides: Oliver, Andreas, myself, and Fabrizio. Okay, so in terms of roadmap, last year I had a similar presentation about integration of Xcache, external storage and file adoption, and more details can be found in last year's workshop. And this year I want to talk about QoS data management and the converter engine. And remaining in 2020 would be a final release with all of this. Okay, so what do we mean by data management? Well, there is this goal that depending on the storage use case, you want to provide a storage policy which will have the cheapest, will be the cheapest solution, have the lowest cost. Okay, and storage policies, they can be either according to system rules or maybe even user-defined. And concretely, to reach this goal, we have implementation of QoS classes and also the converter engine now, and I will explain how all these tie together. But first of all, just to give an example of what I mean by a storage policy, for example, we want to store a file in a replica or erasure encoding format. This is already a storage policy. Each file has 2 replicas, let's say. A more advanced storage policy would be files unused for 6 months would be stored in erasure encoding. This is also one storage policy. Even more advanced would be unused for 6 months and larger than an arbitrary size, because it makes sense for larger files, but not so much for smaller files. And even more advanced would be automatic transitions to tape if inactive for a certain amount of time. But okay, that's kind of the holy grail, and let's say that will be more for the future. So implementation, QoS classes in EOS. Basically, we already have storage parameters, the so-called storage properties, which in EOS are the layout, the replication level, the checksum. A QoS class is just an abstraction on top of this. But it is discoverable. You can query a system and ask what kind of QoS classes it knows how to speak. It is configurable. You provide, as an administrator of the system, you can configure QoS classes, and they will be loaded up at boot time, and also can be user applicable either on a per file or per directory basis. Of course, to maneuver all of this, there is implemented a QoS API. And another important thing about classes, they allow transitions. You can transition from one class to another. And talking about transitions, I actually have an example here where, let's say we have two QoS classes, disk and tape. You can allow a transition from disk to tape, but no transition from tape to disk, for example. This is, of course, just an arbitrary example. But would be that once a replica goes also on tape, you will never remove it from tape just to have it on disk. But you could have tape into tape plus disk, which would be a different class. And the QoS class encapsulates these 4 storage parameters: the layout, number of stripes, checksum, and placement type. And it also provides guarantees. This is more in the format, let's say if you were to develop a standard format around storing sites, you also need to speak a certain language which we chose to be CDMI. And this one has certain redundancy levels and geolocations. But for EOS, we're interested in the transitions and the storage properties. OK, so I will speed a bit through it. Every file, you can deduce its QoS class at runtime, depending on the 4 storage properties it has. If a file has a QoS transition, a new extended attribute will appear. And this lives for as long as the class is mid-transition. If you put a class from replica to erasure encoding, until that file actually gets put into erasure encoding format, it will have a QoS transition enabled. Every QoS class applied on a directory, this propagates on all the files in that directory. And let's say if you were to open a file with some opaque info, you could specify the desired QoS, if the system allows it and you have the proper permissions, of course. Like I said before, this would be the general structure of a QoS class with name, transitions, and the storage properties, the storage attributes. And also the metadata makes it compatible with a QoS specification. I will skip a bit to it. This is an example of a real QoS class, which I named disk plane. It's on disk. It only has one replica. And it can transition into disk replica, which supposedly is also stored on disk, but may have multiple replicas. To actually know what disk replica means, we'd have to query the class to see the description. How all of this fits into one picture would be this, pretty much. You have the CLI command, and this one allows you to interact with the MGM and query, for example, the status of a QoS class to describe it. And also, given a certain file, I named it empty file or directory, you can get its QoS class or even set it. MGM boots up. It loads the QoS class's config. And then it has the QoS API, which allows listing of properties, retrieving just one property, or setting a QoS class. If you set a QoS class on a file, it will trigger a conversion into the desired QoS class. So now we arrive in the second part, which is the converter engine. What I mean by this is actually it's a rewrite of the old converter daemon. It pretty much takes a file, it does a third-party copy, and rewrites it in the new desired layout, replica, checksum, and scheduling policy. And this one, you don't have any more one converter per space. Now all of it is centralized, and you only have one converter daemon, which is actually a thread pool. All the jobs are stored persistently in QuackDB, so in case your MGM restarts, you can still retrieve the same jobs and continue where you left off. Jobs are fetched in batches of 1,000, and it takes one batch, processes them as it goes on, If a job fails, it puts it back into QuackDB in a different table. So you can always have a